All right, we're going to look at another way to get the particular solution for a second-order differential equation. It's going to be important to recognize this has to be a linear equation, and this is specifically for a second-order differential equation. It can be generalized for higher order, but it requires non-trivial changes. So we are assuming we have a differential equation, second order, and it's of this form. And it's important to recognize that these terms can be functions of time. So at this point, if you have a differential equation and you have functions there for time, other than for Cauchy-Euler, there's not much you can do other than use variation of parameters in terms of guessing. Even if you have Cauchy-Euler equation and it's non-homogeneous, you're kind of be limited to using this method for finding the particular solution. So we're going to proceed just as we did before. And the very first step is always to determine the homogeneous solution. And we're doing that because this is a linear equation. If it's not linear, then this isn't going to work. And so we're going to assume that you go through and you find the homogeneous solution. And we're going to call those two functions, and this is the key thing, it's second order. So for our homogeneous solutions, we need two different homogeneous solutions. Okay, and then for the second step, just as before, we're going to determine the particular solution. And now this is where it's going to be a departure from what we've done before. And I should say this is going to be very important to note something here. This is different than what is in the book. And it's different from most of the things that you see on most online resources. And where it's going to be different is that term in front of the second derivative. The book assumes that you've divided through by the R of t and you have a coefficient of 1 there. And most other resources do the same thing and assume that there's a 1 there. I'm going to do this in a more general form and keep the R of t there. And if you memorize formulas from the book or you memorize formulas that you find online, this is going to break down because of this one difference. So be very careful in how you do this. And we're going to use now something called the variation of parameters. And it's going to be very similar to what we did before with the reduction of order. So the same idea, but where it's going to be different is now we have two homogeneous solutions, whereas before we only had one. And the question is how do we deal with this situation now for the second order case? And it's going to be important to recognize that we have, we're looking for one equation, and we're going to have two unknowns. And those two unknowns are going to be products with the y1 and the y2. And so we have two unknowns. Right, so if we have two unknowns, we need two equations. And at some point, we're going to go back and plug our solution into the original differential equation. That's going to be one equation. And for the second equation, there's nothing offhand that we have to enforce. And so the only thing that really matters is whether or not we solve the differential equation. What we put here does not matter. And what I'm going to end up doing is I'm just going to make something up. I'm just going to make an arbitrary, it's going to seem like it's arbitrary, but of all the choices we could make, it makes things much easier. And it doesn't matter what I choose for that second equation, as long as the differential equation is satisfied, life is going to be okay. So there's going to, at one point, I'm going to just I'm going to set some terms equal to 0. And the reason I'm going to do it is because if I have two unknowns, I need two equations. And I'm going to make up an equation that allows me to do things nice. So for my particular solution, now here's the thing, is when we did reduction of order, we took a homogeneous solution and we just multiplied it by some function and plugged it back into the equation. So we're going to do the exact same thing, but because we have a second homogeneous equation, I'm going to make use of that second equation and do exactly the same thing. So what it matters here is that I'm assuming I have y2 and y1 because I've taken this step to determine the homogeneous solution. Given that I have y1 and y2, I'm going to make up a new system of equations for v1 and v2. And because I have two of these things and I have one equation that needs to be solved, I'm going to have a problem. I'm going to have to make up a second equation because I have an unknown for v1 and an unknown for v2. And keep in mind, y1 and y2 are functions we know. Okay, so just to make that explicit. At this point, we know y1 and y2 of t. We do not know v1 of t and v2 of t. Our whole goal is to figure out what those are, and I'm hoping that the process of calculating v1 and v2 is going to be easier than just working with the original equation by itself. And sometimes that turns out to be the case. If you try this and it looks like a mess, normally what you do is you just stop and try something different. It's perfectly fine to try things and then say, there's got to be a better way. So we have two unknowns, v1 and v2. We have one equation, and that's the original differential equation, which is r times y double prime plus p times y prime plus q times y is equal to some function g of t. We need at least one other equation. Okay, and because we need this to solve, if we have two unknowns in one equation, what we're going to do is we're just going to make something up. But we're going to make something up that makes the process as easy as possible. All right, so what are we going to do? We're going to go through and look at this process in general. It's going to be a mess, and then in a separate video we'll look at examples. And we're going to actually have a second day of just nothing but examples because it looks pretty weird at first. Okay, so the idea is this. My y of t is equal to v1 times y1 plus v2 times y2 of t. I have a differential equation that looks like r of t times y double prime plus p of t y prime plus q of t y is some g of t, and I'm assuming r, p, q, and g are all given to me. And let me just be explicit, y1 and y2 are the homogeneous solutions. So I'm going to plug yp into the ODE. Now in order to do that, I've got the function, I need to take its first derivative and its second derivative. To take its first derivative, right, so I'm working now with this function. I have to use the product rule because I have v1 times y1 and v2 times y2. So I'm going to have v1 prime y1 plus v1 y1 prime. And now the derivative of the second term is going to be v2 prime times y2 plus v2 times y2 prime. Okay, so we have 4 terms. And I know that when I plug this into here, I'm going to have one equation, but in the back of my mind, I know I'm going to need one equation to make up things later. So I am going to shoot my ammunition now and just use it. So again, I can make up anything I want. Now note, if I take another derivative of this, I have to use the product rule again. I'm at 4 terms. I'll have 8 terms, and I don't like that. And when I do that, I'm going to have second derivatives of v1 and v2. I don't like that either, because having 2 derivatives and working with those things is challenging enough. So here's what I'm going to do. And again, I'm just making this up. I would really like that to be as simple as possible, so then I can just focus on those 2 things when I plug it back in. So I'm just going to arbitrarily let v1 prime y1 plus v2 prime y2 equals 0. Right. And so that's my second equation. My first equation is going to be the differential equation. Okay, so I'm just going to arbitrarily let that be the case. And again, it doesn't matter. I could make this equal to t. I could make anything up that I want, as long as the original differential equation is satisfied. But the reason I'm going to make this up is that my y prime now, these 2 terms cancel, and I'm left with v1 y1 prime plus v2 y2 prime. And I'm assuming I know y1 and y2, so I can take their derivative and that's not a problem. So now when I take the second derivative, I'm going to do the product rule the first as v1 prime y1 prime plus v1 y1 double prime. And now the product rule in the second term is going to be plus v2 prime y2 prime plus v2 y2 double prime. Okay. So given this for my y, this for my first and second derivative, I can now plug it into my differential equation. So I'm going to have r of t times y prime, or y double prime. So it becomes this whole mess. It's v1 prime, y1 prime, plus v1, y1 double prime. Then I'm going to have plus v2 prime, y2 prime, plus v2, y2 double prime. So that takes care of this term here, plus p of t times y prime. Y prime is going to be now, so since those are 0, I'm just left with this term. Gives me v1, y1 prime, plus v2, y2 prime. And then finally, plus q of t times my y, which is up here, is my v1, y1, plus v2, y2. And I know that has to be equal to g of t for everything to work out. All right, so that's a mess. So what did I do? I had my assumption. I have my differential equation, which was given to me, so I know r, p, q, and g. I know how to get y1 and y2, I'm assuming. So I'm assuming I have y1 and y2. I take that and plug into my differential equation. But because I have 2 unknowns, I need a second equation, so I just made something arbitrary that makes things easier, and I get this huge algebraic mess. Keep in mind that y1 and y2 are solutions to the homogeneous equation. So what do we have? So let's write this all out. I had an assumption that yp is v1, y1 plus v2 y2. y1 and y2 are solutions to the homogeneous equation. So that means r of t y1 double prime plus p of t y1 prime plus q of t y1 is 0, and r of 2 y2 double prime plus p of t y2 prime plus q of t y2 is 0. And that's just definition of what it means to be a homogeneous solution. Okay, and I plugged these into a particular solution, and what I had r of t times the quantity v1 prime y1 plus v1 y1 double prime plus v2 prime y2 prime. I'm dropping the t notation just because it gets tiring and it's a bit of a mess. So I get v2 y2 double prime plus p of t v1 y1 prime plus v2 y2 prime plus q of t times v1 y1 plus v2 y2 is g of t, and I've also made up an equation that v1 prime y1 plus v2 prime y2 is 0. So that's my equation 1, and that's my equation 2. All right, so I'm just going to expand this out as far as I can go and then start collecting terms. So multiply the r of t through. So I get r times v1 prime y1 plus r times v1 y1 double prime plus r times v2 prime y2 prime plus r times v2 y2 double prime. Okay, so now I'm going to have plus, oops, be careful here. Yeah, let me keep the v1s and y1s alike. So this is going to be plus p of t v1 y1 prime plus p of t v1 y1 prime. Oops, that's that term. Sorry, this term needs to be p of t v2 y2 prime. So that term is here, p times that is here, and that was a mistake, sorry. Now for this term, it's going to be plus q of t v1 y1 plus q times v2 y2, and this all equals g of t. If I look at that equation, r v1 y1 plus p v1 y1 plus q v1 y1, that is this equation here times v1. If I factor out a v1, I get r y1 double prime plus p y1 prime plus q y1. That all equals 0. And the same thing is going to happen here. Right? Notice there's a v2 everywhere. I can just factor that out. That becomes the second equation, r y2 double prime plus p y2 prime plus q y2. That is also equal to 0. So I'm only left with this term and this term on the left. So my equation 1 becomes r of t v1 prime, and again I know r of t and y1, so I can calculate everything except for the v1 prime. I don't know that. Then the second term is r of t v2 prime y2 prime has to equal g of t. And this is now my equation 1 to solve. So I now have 2 equations, 2 unknowns. And let's see, so my first equation is r of t y1 times v1 prime plus r of 2 y2 prime times v2 prime equals g of t. And then the second equation is the v1 prime plus y1 v1 prime plus y2 v2 prime is 0. My two unknowns are v1 prime and v2 prime. Right, so I can now solve for v1 prime and v2 prime, and once I do that, I integrate to get v1 and v2, and then when all that is done, my particular then is going to be equal v1 times y1 plus v2 times y2. All right. In a separate video, we'll just start doing some examples. But the important thing is once you get it down to there, you just grind it out and turn it into integrals and some algebra. The other thing to note is that, again, this is different than what's in the book and is different than what most of the things you'll see online. Online, all those formulas and stuff that are put out there assume that R of t is equal to 1. So you would have to manipulate the equations to make that happen. And the formulas they derive are assuming R of t is 1. And so you have to be very careful with that.